So good morning to those few of you who are here. I did not expect too many, so therefore I made a cup of coffee just to give you a little bit of, but I can see some of you also brought already. But anyways, to the last drop, and if you need more, I think I can find more. I think today is the right day to do stuff like that. So how did it work out with the last assignment? I have not had many questions for the last few days. There were some questions early on, and I mean, for me, that's a good sign. It means you got started soon enough to get things done. Main comment, I think, was you could make an awful number of graphs. And I think one of the tricks is how many do you actually need? In the break, I'll discuss the feedback that you gave me in the course evaluation, or after the break, but I prefer to do it without streaming, so that's how things are. Just because I don't want to have that stored out there. But you can say the purpose of today is basically to connect things. So it's reaching backwards to how things were, by stepping forward again. So we're trying to kind of say, well, why, when you look at data, this is the heat consumption in the VEX area with the black lines, and then the front is the temperature. So whenever time progresses, we get more information. But there's also sometimes that systems does change over time. I mentioned it briefly last time, but things does change. And, well, what should we do? First of all, whenever we get a new observation, we should not recalculate everything. When did I say that the first time? How many weeks ago? Roughly a number between 0 and 12. I think I said it the first time during the third lecture, but around that time. What was we were doing that time? We were looking at linear trend models, where we basically said whenever you just add a new observation, you don't have to recalculate everything, you just have to add what comes into the system design matrix from that past most recent observation and add that to the previous stuff. And we should also keep in mind that models are approximations, and they are all wrong, but some are useful to add to the quote. So again, if we have approximations to things, they may change over time because there are some things in the underlying system that we do not include in the model. A classical thing, I think the first time at least where I was exposed to this, I guess you've all heard about wind turbines, and you all know that it's good when the wind is blowing because then you get more power production. But when you have turbines on land relative to turbines on water, do you know what the difference is? Except they're more expensive to build on water. Have you considered why do you place them out at sea rather than on land side? Well, noise is of course one concern, but that's not what makes the money. The money comes from the power production. When you're out at sea, you have less so-called roughness, surface roughness. That means that the wind at whatever elevation you're up at is more stable and less turbulent. When you get on land, you can actually see if there are leaves on the trees or not, if there's a forest nearby from the power production. So you have a seasonal change in the wind speed dependence relationship to the power production. Stuff like that, you don't want to build that into the model. Then you also have to re-estimate your model whenever someone is building a house a few hundred meters away. Most likely people will not do that, but I mean the trees are growing anyhow. That also creates a disturbance. It's the same thing you do when you're at a bus stop on a windy day. You're standing next to someone or something to get sheltered. It's effectively the same thing. You're not standing out on the shore and just standing out there in the front if it's a windy day and you kind of want to stay warm. A wind turbine is just exactly opposite of that. So just to say that things does change. And it's also, you can say, whenever you want to develop something for real-time applications, you want to learn whenever new data becomes available. So stepping backwards, what have we been doing? We've been doing, you can say, ordinary regression models, just to get a common basis. We can have a final impulse response where we have some input view here, and then we have some noise, and we have a mean value structure, and we can have a model, a linear system, where you just have a final impulse response. Okay? These are models, autoregressive models. We know that we can solve those by means of ordinary least squares. We can also have, you can say, a combination of those two, where you both have an autoregressive part, and then you have an input part as well. We've also played with those models a couple of weeks ago. All these models can be estimated by linear regression. The only class of models where you cannot do this is when you have a moving average part. So in all these models, you just have an epsilon. Now, the R up there stands for recursive, as to how do we do recursively update our estimate of parameters whenever we have new observations. In all these models, we can write it. Here's just a combination that you can have a mean value, you can have some autoregressive, you can have some input, and you have just those things as columns in your design matrix. What we will do is just to call, you could say, all these x's up here, and then it's just an ordinary linear regression problem, where the regressors may be past observations, past input, and so forth. It's all things that are known at a time and point where you have the most recent observation. Given this, given some observations, we want to do least squares. We want to minimize that and find the theta. So I think that this is the last time I'll ask this question. What is the solution to this? The inverse of X transpose and X. We don't need a sigma inverse now, because we're not doing the weighted. We're just doing the ordinary. So we have X transpose X and that inverse, and then X transpose Y, exactly. So that's the good old fella. So what we did in the trend models was to realize that whenever you get a new observation, you basically just add an extra element in the sum. So you add something for this part, and you add something to this part. So what we did was to have the RT as the outer product of the design matrix part here, and then we have HT that say, well, how is that related to the observations? So that was what we did. And we can do the same thing for a generic regression model as we did for the trend model. Basically, the trend model was just using time as regressor instead of using other states and things. But it's flexible. It doesn't care what the input is. It's just you to make the educated choice. So we can update RT as XT transpose plus RT minus 1, and we can update ht as xt on the observation yt plus h of t minus 1. And then we can find an estimate of theta hat at time t as the inverse of rt pre-multiplied on ht. So this is pretty much what we did a long time ago. We just rephrase it in a different setting. As we did last time, initialize with appropriate zeros and don't invert RT until it's invertible. So you need a few observations before you can estimate a linear regression model. I think you should all know that by now. We will all make the coding error, and then we will see that, okay, I know why. And then we will fix it and then make it work. So what we just briefly mentioned back then was that rather than keeping track of all these matrices, we can actually eliminate one of them, the H here. So how does that work? If we look at theta t from down here, what is that? That is the inverse of RT on HT. And then we can take HT and say, well, what is that? We have the inverse of RT, and then HT is given down here. It's XT YT plus HT minus 1. And when we have HT minus 1 here, how can we reformulate this? Given that R is well behaved, and we assume it is because that's also the foundation for the variance that we have later on, then we can just reorder this by pre-multiply by, and it's RT is symmetric as well, so we can pre-multiply by RT, so that RT theta hat T equals HT. So that means we can insert RT theta T in place of HT up here, except that we have to keep track of the time index. So we should have RT minus 1 theta hat T minus 1, like that. Now, what I want to get to is an update of theta t, and I don't want to keep track of different values of RT. But RT minus 1, what is that? Well, we can take XT transpose here and move that to the left-hand side, and insert that in here. So that gives me an RT inverse XT YT and plus parenthesis, what we have there is an RT minus lowercase xt xt transpose, like that, and then that should be multiplied on theta hat t minus 1, parenthesis close. Next part is to just multiply in here, and I'll take it in 2 steps. So we have the RT inverse, and then we have XT YT plus RT on theta t minus 1 hat minus XT transpose on theta hat t minus 1. And now looking at these terms, we have RT inverse on RT. So let's first take this term out and write that this is equal to just theta hat t minus 1. And then this has an RT inverse, and both this term and that term, the only remaining terms, have an xt as the leading part. So we can write it as, and have the same sign as up there, plus RT inverse on xt. And then what do we have left? We have a yt there, the observation, minus xt transpose. Oh, did I make a typo here? No. On theta hat t minus 1. Basically, what we have out here, that is the prediction error. It's the observation minus what we predicted with the previous estimate of the coefficients, with some kind of gain here. How much to update? Does this remind you of something? What does it look like? Exactly, it looks like the reconstruction in Kalman filter. So all these things are connected. That's the important part. Now, if we want to go further than this, for small models, it's not a problem to make the inverse of R all the time. It's a low number of calculations. If you have things that are numerically unstable, that means R becomes close to be singular, then you can rewrite it actually defining a Kalman gain in this way, basically, and then having something that represents the inverse of R matrix P here. And when you just look at it, why use something with that many terms in when you have something that's simpler at top? That's at least the first thing I thought of when I saw this. And you can say the reason is, when you do this, basically comparing with what you have over here, it's just RT inverse. That's the whole fraction pt minus 1 divided by 1 plus x transpose pt t minus 1 xt. So what you have there, basically, what is you have to realize is that this element there is a scalar. Plus a scalar, still a scalar, so you divide by a scalar instead of having to make the inverse of a matrix. So if the dimension of your model is large, you may prefer not to invert R all the time, also because of potential numerical issues. So, and if you do the math in that, it actually also means that the number of operations needed is less, even though you have more terms involved here, just because it's simpler operations. And this pre-multiplier here, it's the same part that is down here. So you just have to calculate it once. So it's not a huge calculation. But the structure is the same as you have up here. So again, this depends on whenever you're going to implement something. Is this a challenge or not? Do you have all the time you need to do the calculations? This is much easier to kind of debug, I would say. And also the understanding of RT as being the design matrix that you just update, I think is more convenient. But that said, if you want to make things more robust, you have an alternative. So to go back to the heat consumption here, the hourly heat consumption, and looking at the ambient temperature, somewhere reasonably representative of this flat place here, I think we can all see and not be surprised by the fact that whenever the temperature drops, the heat consumption increases. That's hopefully not a huge surprise. There's one more thing to it, which you may not see. What happens when it's warm outside? Yeah. Exactly. When it's warm outside, there's much less variation in heat consumption. Basically, to a degree where the heat consumption does not depend on what the outdoor temperature is. Well, how many of you kind of look into how your house is heated? How much heat do you get or use from, say, May to August from your radiators? You still take showers, that's fine. Please do that. But how much heat do you use? Well, a dorm's shutting off the heat because they don't want you to kind of just open the windows to control the heat in the Russian way. I think that's actually to some degree appropriate. However, I remember from my days at a dorm, October 1st is not always the appropriate time to turn on the heat. I don't know, it's still the same thing. It is or isn't. I remember having to kind of find a way to heat the room because I was at the end of the hall and it was getting freezing cold the last week before they turned on the heat. Because they did it based on the calendar and not based on the outdoor temperature. We want, of course, to do this in an intelligent way to use heat whenever we need it. If we do this, run the algorithm from before, we get an estimate of the intercept. So when it gets to be winter, it increases, and the slope becomes more and more negative. And a negative slope means when the temperature is increasing, the heat consumption when the temperature is increasing, the heat consumption decreases. So that makes sense. Initially, there's a very small slope because it really doesn't matter. And then at the end, it increases. Now, what is the problem here? Can you see that? The data we have here is for a full year, starting somewhere, I think, around May or June. What is the problem here? Yeah?
It doesn't go back.
Exactly, it doesn't go back. I have an adaptive, I have a recursive update of the model, but I don't let it adjust to only the most recent path. I adjust to everything at every point in time. So, getting back to what you said initially, as the solution, we need to have the weights in here. And basically, this is the same as we did the local trend models. We can have, the one difference here is that in general, you can have the weights to be function of time. And if you have the, you can say, appropriate structure, I thought I had that here. You can have different functions for how to estimate the forgetting factor depending on the current and the past time. The typical thing is to just use lambda to some power corresponding to how many lags is backwards in time. That's the usual suspect, and that's the graph that we've used for the trend model as well. But if you can write it in this form so that it depends on something at a time, so that it can be time varying, then it's also something that you can write in this way and update the estimates recursively. And we should just stay with models and algorithms where we can update recursively. That's the important part. So as for the trend models, everything here is pretty much just the same. We just add a forgetting on the design matrix part, and we forget the last observation. There's one difference here. I don't know if you recall the time, the trend models. The difference was also there for the non for the version without forgetting. It's okay if you don't remember. What you were doing in the local trend models was to shift time backwards. You had the L operator involved here. So you shifted the previous, you shifted the previous xt on yt, you shifted that backwards in time, because now you changed your reference time to be a new time point. Everything was always relative to the most recent observation. Now we say that we have some predictors, and we place them accordingly, appropriately, and that means we don't need to have that shift in time anymore. So that's the only main difference to how things were in the trend models. And you can go through all the calculations over there again. We just have the lambda out there. That's the only thing that remains. So basically this means that the design matrix gets less and less information, but all the rest remains the same. And we can also do it in a way where we're going to divide by scalars. In this way, it's just some ones that were there before that becomes lambdas. So that also makes intuitive sense, because a lambda equal to 1 is infinite memory. So to some extent, that actually works. And you can make this even more complicated if you like to, but I'll get back to that. So what we'll deal with is mostly the constant forgetting factor, and as we saw for the trend models, how you can deal with this is basically to consider what is the effective memory. 1 divided by 1 minus lambda, that's, you can say, the sum of the weights that you used. So that's the effective number of observations that you have. And then you can say, how do we find an optimal value for lambda? We can find one, or how would we optimize it? What we've done previously is to look at the sum of squared one-step prediction errors. That works again. It's kind of one-step prediction errors, I would say in this course, that's one of the things that is almost always an appropriate answer to questions regarding how to optimize. But, I mean, of course, if your criteria is to do something different, then you should do something different. Just as we also did for the simple exponential smoothing. If you look at 1 or 7 or whatever step predictions, you should optimize whatever you want to use it for. So the challenge here is that you may want to have different lambdas for different parts of what you're asking for. So if you both want a 1 and a 2 and a 3 and a 4 and a 12-hour prediction, then you may need to have different lambdas. So that's where things start to get a little bit complicated. Not as such from the modeling perspective, just the bookkeeping whenever you're implementing it. And as before, if you want to optimize things, you should leave out the initial observations just to make sure that things are stabilized. The one thing that you can do to complicate things is to introduce so-called variable forgetting. There are many schemes for doing this. This is, I would say, one of the simpler ones. Basically saying that the criteria, the sum of squared predictions, say I want to have that and target that to a particular value. So if you run through the filter with a particular value and you find S as the sum of squared prediction errors, and then you figure out what should I do in order to keep that at a constant level. Then you can use this. So you have your target here, and then you look at how is the uncertainty, how is the information that you have, or to use as denominator on what is the most recent one-step prediction error. So when you look at this, These are the predictors for the most recent observation. These are the errors. Then, in order to make this work in practice, you want to have a lower bound on lambda, because it says 1 minus something divided by something that is reasonably stationary, and then on top of this you have an epsilon square. Now, assume that you have things that are Gaussian, assume that things are well behaved. What is the likelihood of getting a large error? Well, it's at least not negligible. It will happen. There will be one epsilon that is greater than all the others within your data set. What does that mean? That means that sometimes, unless S0 is very large, but you don't want to have it too large because then you just forget too much, or too little, sorry. Then you will have, if you implement it without having lower bound, you will end up having negative lambdas. I've been there. It happens if you don't handle it nicely. And then, of course, you should pick your S0 according to what you want it to be and what performs well. So to get back to the data, temperature and heat consumption for the VEX district heating network, if we do it with a large lambda here, what is the effective number of observations in this case? How many hours do we use? How many hours does this correspond to as effective memory of this system? $200, yes. 1 divided by 1 minus this number. So basically 200 observations, that's roughly 8 days. So we're looking at the past 8 days effectively. Of course, there's memory further back than that, but effectively it's the last 8 days that is used. And then we do, as opposed to before, we do see the winter, and then the spring term, the coefficient starts to change. But what we also see is that all of a sudden, the estimated slope here becomes much more varying, right? So we gain some and we lose some. But the predictive power out here is much greater. And what happened there, maybe we'll have time to get back to that. So that's what we can, didn't have it for a, let me skip a couple of slides. No? There's something missing here. I'll find that. What there should be here, where did that go? What there should be here is what do we do if we do adaptive memory? What happens then? I'll take that after the break and then I'll find it because I know it's there. So all we've done so far is when we have models that can be written in the usual form of y equals x theta plus some epsilon. Now, what we also saw in the previous part here is that we can do a lot of nice stuff if our model does not depend on the previous epsilons. But we also know that there are cases where we want to have kind of a moving average part. So what can we do in those cases? We can do what is called pseudo-linear regression. Pseudo in the sense that, well, we can use our previous prediction errors as the future epsilons. I mean, as the past. In the future, we can use previous epsilons as predictors. But they will be functions of the parameter, of the estimated parameters. Because when you look at the prediction error out here, it depends on the actual parameters. So that's, but we can still use it as an estimate of epsilon given that parameter. So that's basically saying that in those cases where you have epsilons, previous epsilons as part of your design matrix here, then it becomes a function of the parameters. All of a sudden, it's a nonlinear optimization problem. What we will typically do is to solve it by iteration. So if we want to do it with memory as well, what we do is that we forget the past and we add the squared one-step prediction error for the current time. And then we run that, and the algorithm for the recursive pseudolinear regression model is exactly the same as before, except that now the xt here depends on the theta. And that means that we have to calculate xt. We don't just get it. And if we do it by updating this way, well, we use the most recent estimate of theta to get a prediction error, and then we can repeat that step as often as we like. Now, I think I should take an early break and find the slides that are missing. So let's just resume 10 minutes to 9, and then I'll find